This is Jake White, and this is my Physics Lab 5. In this lab, we will be investigating Faraday's law. So, introduction. In this lab, I'm going to measure and analyze the electric and magnetic fields created by a bar magnet falling through an aluminum tube. Then, using Faraday's law and measurements from the experiment, I'm going to create a computational model of the experiment using GlowScript. And on the right, you can see the experimental results, and you can see that the average time for a bar magnet to fall through the aluminum tube was 2.45 seconds. And at the bottom, you can see the structure of the presentation. So here's the fundamental physics principles: magnetic flux, Faraday's law, the Biot-Savart law, Lenz's law, and Newton's laws. Here's the materials that I used for the lab. I used a smartphone, bar magnet, a roll of aluminum foil, and a meter stick/ruler. So here's the basic physical model of the lab. So the motion of the falling magnet creates a magnetic field that grows in strength as it reaches closer to the ring. Cylinder is represented as a stack of rings. The magnetic field, due to the induced current, points upward, opposite the direction of d flux dt, and this means by the right-hand rule that the current will flow counterclockwise. So here's the procedure for the lab. So first, to make sure that there are no ferrous metals in the environment around your experiment, and then measure physical properties of the aluminum tube, such as its length, wall thickness, and inner tube radius. Then video the bar magnet starting from above the tube to when it exits the tube. Analyze the video and measure the time it takes for the magnet to exit the tube, and repeat 5 times. So here's the initial measurements of the aluminum foil tube. Its length is 0.4572 meters, width is 0.025 meters, inner radius is 0.023 meters, the magnet is 0.023 kilograms, and the dipole moment is 2.43. Here's the experimental data. As you can see, the average is 2.45 seconds. Here's the GlowScript code. So on the left, you can see the physical constants and basic graph initializations, then the geometry of the tube, and numerical parameters of the simulation. And then on the right, you can see where the aluminum foil is created as a series of rings. Then we initialize the magnet. And then on the next slide, you can see where the Biot-Savart law is used. And then below that, magnetic flux is calculated. On the right, we have some position updating, and the force of gravity is initialized. And then the magnetic force is calculated from the tube on the magnet. So here's some further calculations, finding the force, the magnetic force on the magnet and the ring. And then we have the net force, which is the magnetic force and the force of gravity. And so these are the results. And we got that the time in the tube is 2.685. And then you can see the velocity versus time graph. So what if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? So the magnet would take longer to fall down the tube due to the induced current approaching infinity by I equals EMF over R. And the increase in induced current will lead to the magnetic force being increased. What if holes or slots were cut into the tube? How would this affect the ring currents in your model? There would be lower magnetic flux due to the area being decreased, leading to the magnet falling faster through the tube. And that concludes my presentation.